Thank you for that great introduction. So I'm going to be talking today about graph data science. What is it? Why do it? Neo4j's graph data science library, what's new in our latest release, and some real world use cases before my colleague Stuart does a quick live demo of what this stuff all actually looks like in practice. So before I dive into, what is our library, what are our capabilities, I like to start off with just some motivation. Why are we talking about graphs and data science? What do they have to do with each other? And I think a really good motivator is just starting from the viewpoint that everything is naturally connected. If you think about whatever domain you work in, whether you're working in drug discovery with genes, chemicals, and diseases, or supply chain with different suppliers and different parts being manufactured, or if you work in retail with people buying items, right? There are relationships between them. So if you think about, where a lot of this started, we think of social networks, people who know each other. You can kind of build on that and think about transaction networks, right? People buy items, maybe items are manufactured from parts. So you're looking at supply chain risk management, or kind of the classical use case of knowledge graphs, right? Where you have heterogeneous topics that are connected conceptually to each other. Let's say you have a person in this example likes a sport, soccer, football. I'm not going to take sides there. Someone plays that sport. Soccer is a sport. That person lives in a country. You're connecting up these really different ideas in a way that you can reason about them. And it's how people think about things. It's how the real world is structured. But in data science, we typically live in a world of rows and columns. So one thing that's really evident that we've learned is that relationships, those connections we talked about in the previous example, are some of the strongest predictors of behavior. Some examples I like to talk about in James Fowler's book, Connected, is like, how do you know if someone's going to vote or not in the next election? It's not how old they are, how much money they make, it's whether or not their friends vote. If you want to know if someone's a smoker, we're all data scientists, you'd say, okay, I'm going to predict it based on their demographic data, where they live. It's actually if their friends and family are smokers. Those relationships are really strong signals, but you can't predict things that you can't represent or see. So most data science techniques ignore relationships. So if you're thinking about, I'm in Python, I'm using a pandas data frame, what is that? That's rows and columns. It's really hard to manually engineer connected features from tabular data. So if you've done feature engineering, and let's say you've got a data set of people with demographic data and you're going to predict something, maybe you could manually engineer one hot in code, like, is this person friends with another person? But it becomes really painful really fast. But graphs, on the other hand, are built on relationships, right? You have nodes, those are your people, places, things, and you've got relationships that connect them. And graphs treat those relationships on the same level as your data points. So once you're using a graph, you don't have to guess at those correlations or the connections. With graphs, those are built in. They're inherent in your data, and you can reason about them for analytics, running algorithms, or data science, building predictive models about how the structure of your graph will change. And this isn't just Neo4j finding a new use for a graph, right? So according to Gartner, graphs form the foundation of modern data and analytics. Graphs are really important to allow users to represent their data faithfully, build accurate and predictive models, and have explainable models. Gartner found that graph techniques are increasingly prevalent as AI maturity grows, going up to 48%. And if we look at company adoption, there was a great survey that said something like 90% of companies wanted to adopt graph techniques in the next 5 years. So there's a lot of excitement from the perspective of people understand that graphs are useful. And it's really cool because it's coupled with this boom in academic research, right? So if you look at the number of papers published on using graphs in machine learning, they've been growing nearly exponentially. If you look back in 2010, you have 205 papers. If you look at last year, we have over 6,500 papers. There's a tremendous amount of research in this space going into understanding how can I use graphs? How can I do better machine learning with graphs? And then at Neo4j, because we're the graph company, we've seen this exploding interest as well. We have a graph algorithm book that's had over 190,000 downloads. We have a really large and vibrant community of users who use our library to solve data science problems and contribute to our library. And I'll talk more about that one later. But you've got an industry trend, you've got academic interest, and you've got a really excited community of data scientists using these techniques. So when we talk about graphs in data science, what am I talking about? And really, when I think about what is data science is just using data to answer questions. So when I say graph data science, I just mean using relationships to answer questions. And so when you talk about graphs in data science, you could be using queries to find the patterns that you know exist in your data set. I'm a domain expert. I have connected data. I want to find items that were bought by the same people. I want to find someone who's interacted with someone who is made a transaction with a known fraudster, right? I've figured out this pattern. I can find what I'm looking for. Maybe I'm doing feature engineering for my predictive model. Maybe I'm exploring my data. Maybe I'm building a dashboard. Then on top of that, you kind of move into machine learning. And this is, how do we make predictions? And we talk about kind of unsupervised machine learning in terms of graph algorithms, where there's no labels. This is driven by the data. And what you're looking for are the patterns in your data set. What are the outliers? What are the anomalies? What are the trends? How are things connected? What stands out? And the flip side of that is supervised machine learning, right? Where I want to train a predictive model based on some labels. These two nodes are connected. This node has this label. This person's a fraudster. This person bought this item. And you can train those predictive models using your graph data. And so when we talk about machine learning, maybe you're running algorithms for feature engineering. Maybe you're training predictive models. Maybe you're using those algorithms to find patterns for your analytics dashboard. All of those are data science. And then rounding it out, we talk about visualization. So not everyone works with graphs all the time. We're really kind of wired to think about data in tables, right? So it's really important to be able to visualize what you're working with, explore it, collaborate with your team members, and present to folks to get buy-in. What is this? What did I find? Do my predictions make sense? Look at this pattern. And that's where you can use visualization tools like Bloom or Linkurious to explain what you found and kind of explore those what-if scenarios. And if we think about how do I get started, I really like to think about it like a natural progression. So if you kind of start with, if I want to do data science with a graph, step one is having a graph, right? So you want to get that data ingested into your graph database, store your connected data in a connected shape, so you can find the patterns you know to look for in that data. This is those expert-driven domain queries to find out, this is too complicated for me to pull together in a relational database world, but it's really easy in a graph. Then once you've got your graph, once you can interrogate it, ask questions, the real easy next step is graph algorithms. You don't have to have labeled data. You don't have to have, specific things in mind. This is basically letting the graph speak for itself. You can use unsupervised machine learning techniques to identify associations, anomalies, trends, outliers in your graph, and start to understand, I can't spend all day playing with my graph. I can't understand all of these billion data points. What's most important? What stands out? What's associated with other things? Where should I look? And then kind of building on that, getting into the most sophisticated end of the spectrum is really graph native machine learning. And this is now you have labels in your data set. Maybe it's a transaction graph and you've predicted who's committing fraud. Maybe it's your retail graph and you know who bought which item when. Maybe it's an X-Men graph, and we'll talk about that later on, and you want to predict who's an X-Man. This is where you can use graph embeddings to learn the features in your graph that are important, that you don't even know are important yet. And then you can train in-graph supervised machine learning models to predict those labels, to predict who's going to buy what item next, who's committing fraud, who's an X-Man, right? And each of these build on each other. So in order to do anything, you need your data in a graph. Graph algorithms let you find what's important without having those labels. And then once you've got labels, once you've run graph algorithms to generate predictive features, then you can start training embeddings and using supervised models to predict how your graph will evolve. And so you're here at a Neo4j webinar. So how does Neo4j help you with that? We really talk about our graph data science framework. At the heart of it, you have the Neo4j database, which is just stores your graph data in a graph shape. It's native graph creation and persistence. You can run your queries super fast. Then you have the Neo4j Graph Data Science Library, which is what I work on. And that's our scalable graph algorithms and analytics workspace. It's a plugin for the database that lets you run graph algorithms, supervised machine learning in the database, it also transforms your underlying data into the right shape for the problems you're trying to answer. And then we have Neo4j Bloom, which is our visual graph exploration and prototyping tool. And if you think about it, these map pretty well back to that Venn diagram I showed a few slides ago, where we had queries, the database, machine learning with GDS, and then visualization with Bloom. So we try to offer like a full toolkit so that you can get up and running quickly. I work on the Graph Data Science Library. This webinar is about the Graph Data Science Library. So to spend a little bit more time on what it is, there's really two pieces, right? There's graph algorithms and machine learning. And this lets you understand your data, compute metrics about the topology and connectivity of your graph, build predictive models to enhance your graph, and it's all highly parallelized and scalable. But the secret sauce, how we actually get this to run, is the analytics workspace. And that means the in-memory analytics graph that transforms your underlying database. It lets you pick out, this is the right slice of my database. These are the nodes I want to analyze. These are the relationships. This is how I want to transform it. Pulls that into memory into an optimized data structure that lets you run these algorithms lightning fast. Then we have the model catalog that once you've trained a model, you can store those models in the database. You can persist them. You can publish them to your team. Neo4j is a database company. We should be able to store your models. So we've got the GDS library has algorithms and the analytics workspace. If we want to spend a little bit more time talking about the algorithms that we have available, there's really 6 categories of what I'd call like unsupervised algorithms on the left-hand side. And then we have our supervised machine learning pipelines, which are newer. So if we go category by category, we have the pathfinding and search algorithms. And these are the ones people usually think of when they think about data science on a graph. It's what's the shortest path between these two nodes? How many paths are there? Is there a path? Can I reach this node from this other node? Really commonly used in logistics and supply chain. Really kind of first and foremost when you think about graph algorithms. Then we talk about the centrality and importance algorithms. And these are really just different ways of defining which nodes in my graph are most important. And each one of these kind of uses a different definition of importance. So degree centrality is how many connections does it have, whereas page rank is how influential is that node. But each of those will tell you for each node, how important is it relative to the other nodes in the graph. We have community detection, which helps you find which parts of the graph are more connected to each other than the rest of the graph. So in kind of typical data science, you've probably used k-means clustering. This is kind of a similar concept, but on your graph data. So which parts are more densely connected? You could use anything from weakly connected components, which finds totally disconnected communities, to something like speaker listener label propagation, which can find multiple overlapping communities. We see this used really commonly in fraud detection, where you're looking for fraud rings, who's interacting with who. We see it used in marketing and recommendations, where you want to find out who interacts with who, and I can target a specific community. Really useful also for feature engineering. So triangle count is really commonly used as a feature to predict anything from influence to whether or not someone's committing fraud. We also have heuristic link prediction, and these are unsupervised techniques for link prediction, basically based on the connections each node in your graph has. You can give it a pair of nodes and say, should there be an edge between them based on the number of common neighbors they have, how tightly connected they are. We have similarity algorithms, which are some of our most popular. These basically say, given a node in the graph, based on its neighbors, its properties, its relationships, what other node in the graph is most similar? Node similarity looks at neighboring nodes, whereas k-nearest neighbors is built to use our embeddings. And then finally, we have our graph embeddings. These are the kind of secret sauce for machine learning. They translate your graph into a numerical representation that you can then use for machine learning. So we've got 4 embeddings, Node2Vec, FastRP, FastRP Extended, and GraphSage. Each one of those is able to learn different things about the topology of your graph and create a machine-readable representation that takes your 5 billion by 5 billion adjacency matrix and condenses it down into the right 200 numbers for each node in order to be able to perform supervised machine learning. And so all supervised machine learning is we want to predict how the graph structure is going to evolve. Right now, we offer 2 techniques: node classification, so you want to predict a label that's missing in your graph, So it could be this person is committing fraud, this person isn't, this person is likely to churn, this person is not, or link prediction. This person is likely to interact with this person in the future. This disease is likely to be connected to this gene. Basically predicting changes in your graph topology. And we have a lot of other features that make it easier to work with your graph, but this is usually when people say, what is GDS? This is the heart of it. So now that I've covered that, we're going to talk about what's new in the last release. So we just released GDS 1.6 on May 27th. Preview was May 20th, so some of you have probably already tried it out. I'm going to spend a couple minutes talking about what features are new, what's exciting, what's in store. So this release, we kind of have 5 main things we're talking about. We've worked on our machine learning capabilities. So can you persist models? How to use link prediction, node classification. We've moved a lot of our algorithms to our production tier, and that's the fully supported, fully parallelized tier where we've optimized the heck out of them. A bunch of pathfinding algorithms, degree centrality, article rank, eigenvector centrality have all graduated. New implementations up to 25% faster for the pathfinding. Our new PageRank implementation is about 80% faster. So much better implementations. We've introduced subgraph projections to subset your graph. We've spent a lot of time improving our embeddings, and we've got new capabilities like graph filtering, scalars, and more. So I'm going to just highlight kind of the 3 top new features, but also definitely check out our website or release notes to see more. So really exciting for all of you is in this release, we've actually opened up Community Edition to support up to 3 trained models for users. So before, when we had Community Edition, there was a limit to 1 model in the model catalog at a time. So you could train a model, you could use it, but if you wanted to compare multiple models or experiment and see what you thought of the predictions, it wasn't that easy. We've now raised that cap, so you can now have multiple models to compare and contrast at the same time. We really wanted to thank everyone for all the time spent testing our library, giving us feedback, giving back to the community. That's not all. We've also added a lot of tooling to make machine learning easier on your graph. So we added a new procedure for scaling your properties in the in-memory graph, supporting min-max, max, mean, log, standard score, L1 and L2 norms. This lets you, let's say you've got some properties in your graph, maybe you've run some algorithms. Machine learning often works better when you have normally distributed data, or maybe you want to scale everything so that you're comparing apples to apples. If I've got PageRank that goes from 0 to 3, and then I have between the centrality that goes from 0 to 400, I want those to be on the same scale. So we added new procedures that let you scale the properties in your in-memory graph to prepare them for node classification, link prediction, and the graph embeddings. We spent a lot of time working on node classification and link prediction in this release. They now support stream and write modes for the prediction, and models from those can be saved, published, and restored. Previously, that was only available for GraphSage. Now it's available for all of them. We've also spent some time adding additional metrics to node classification, improving our model scoring, really just making those more robust. And also for folks who like our graph embeddings, Node2Vec has been promoted to the beta tier. It's significantly faster than before. It now supports weights, so if a weighted graph, that can influence your embedding. It also supports seeding, so you can get repeatable results. And it has mutate mode, so you can update that in-memory graph and perhaps scale the data so that you can use it for an input, right? So we've spent a lot of time making our machine learning supervised ML part a little bit more mature and making sure it's accessible for folks to use. Another new feature in this version that we're super excited about is subgraph projections. And I think this is something that folks have asked for a long time. I have my in-memory graph. I don't want to run my algorithm over everything in the in-memory graph. I only want to run over a subset of it. Or I want to run my algorithm against individual communities, right? So now what you can do is we added a graph.subgraph procedure that can take your in-memory graph and you can tell it how to filter that graph based on node or relationship properties. So this lets you, let's say, use native projections and subset your graph instead of using cipher projections, which are much more expensive and slower. This also lets you pre-process your data for faster execution. So if you want to calculate degree centrality and remove the very high or very low degree nodes, that's a filter step. Or if you want to run weakly connected components and create graphs for each subcomponent, that's easy to do now, and then you can execute those expensive algorithms on each component. This also lets you start to chain algorithms together based on filtering properties. So what you could do is, let's say you were trying to do recommendations. Maybe you want to run Louvain to find communities, and then run node similarity within each of those communities. Before, you'd have to run Louvain, write it back to your database, reload your data into memory, and kind of that's slow, it's extra steps. What you can do now is run Louvain, subset your graph, so now you have one graph for each community, and then execute node similarity against each of those. So this is really about just making it easier to work with your in-memory graph, making it easier to manipulate it into the right subgraphs for your problem. Then one thing, the final thing we'd like to highlight in our new features is we've actually added the influence maximization algorithms. We've added 2 of them. What they are is basically you want to find the nodes in a graph that can trigger cascading changes. So if I have to pick 3 nodes in the graph that are going to make the biggest change, have the biggest influence to the rest of the graph, which 3 do I pick? And if you think about that in the context of a real world problem, it's I have a limited marketing budget. Who do I market to drive the most adoption? Or it's, there's a lot of websites on the internet. Which one should I read to find the most important information first? Or relevant today is who do I test in a network of people to get early warning of an outbreak? Maybe this is coronavirus testing, or maybe it's water testing. You want to say, I need to put in sensors. I have a limited budget. Where do I put them? Right? This is really about, given a network, figuring out which nodes in that network can spread information the best based on the topology of your network. Or formulating it kind of more mathematically, given a network with n nodes, giving a spreading process across that network, you have to choose a seed set of nodes to maximize the number of nodes that are influenced. And that's what these algorithms do. It's a combinatorial optimization problem, so it's really computationally complex. There's 2 methods that we've got implemented now. We have the greedy method, which is a polynomial time approximation of the problem, and the CELF method, which is a much faster, newer implementation. It's an approximation that's, if you want to run this on a big graph, go with that one first. What's super cool here that I really want to highlight is Neo4j, our engineering team, didn't write these algorithms. These were actually contributed by a community member. His handle on GitHub is xkitias, but it's Xenophon Kitias, who did this work as part of his master's thesis and used our internal APIs to write his own algorithms and then contributed those back to the library. So we are super grateful to have that engagement. And we're really glad to have these new algorithms. And if anyone else wants to work on algos, we've got our Pregel API, we've got our internal APIs, please use the infrastructure that we've built. So I want to just finish before we move on to the demo with some real world use cases. So I've talked a lot about, cool, what's graph data science? What does Neo4j have to offer? What's new? I always like to end on, what are people really doing, right? So I could tell you lots of cool stuff. It doesn't matter if no one's using it. If we think back to kind of those steps I talked about before, I really think about this kind of like a spectrum, right? So we have the complexity of what you're doing, from really simple ad hoc analysis, I'm going to run one algorithm to answer a specific question, to really highly complex kind of R&D type problems where I'm going to build a custom algorithm for my specific problem, run it on giant data sets. And we also kind of look at repeatability, right? So for my project, is this a one-off? Am I just running PageRank once and I've answered a question and I'm done? Or am I going to run these same 3 algorithms every day on the same data set, full production, to make valuable predictions? And all of these kind of count as graph data science, right? We talked about the steps of graph data science. Kind of on the analytic side of things, we look at simple ad hoc algorithms that you're running kind of as a one-off to investigate. And that's really the Boston Scientific use case, looking at improving reliability. If we look at highly complex, we really are kind of moving into the R&D space. And this is where companies like AstraZeneca are using graphs to improve patient outcomes, to recommend drugs to patients based on their patient journeys. And then kind of in the middle, we look at these disambiguation use cases where giant graphs, billions of nodes, running at scale, running the same workload every day to provide value. And that's what Meredith Corp is doing. So spending a little bit of time on each use case, Boston Scientific, kind of a more classic analytics use case, is looking at using graph algorithms for recall prevention and basically root cause analysis. So they have a really complex supply chain of raw materials to intermediate parts to final parts, and they manufacture medical devices. So failures, recalls are really bad. They've modeled that data into a knowledge graph that shows their whole supply chain. And they can quickly now pinpoint the root cause using queries, but they can also figure out what are the wrong combinations, where are the failures coming from. You can use a query to find the root cause after something happened, but you can use an algorithm to predict where are the problems going to be in the future. What parts of my supply chain look most like these parts that have had failures before, or what parts, if they fail, have the worst outcomes. So this is really ad hoc, exploratory, running algorithms to answer questions, but providing a lot of value. When we look at something that's more kind of production scale, we're really talking about Meredith Corp, looking at how do you identify anonymous users on the web. They own a lot of magazines, but a lot of their money comes from advertising, and a lot of that is digital. They have a lot of users who interact with their websites without any kind of logins or accounts so they can be tracked, which makes it really hard to place advertising or make recommendations for what they should look at next. So what they were able to do was import all that web traffic, all those users interacting with the website, the first and third party cookies on their browsers into Neo4j, look at where those cookies co-occurred, and use graph algorithms to create unique profiles. So they took 14 billion anonymous data points and converted that into 163 million user profiles. And then once they were able to look at unique anonymous user profiles, that was able to drive a 612% increase in web traffic. So this is really that repeated workflow where they're running a specific set of algorithms in combination over and over again every day for production value. Then kind of moving over to the R&D side of the house, we have AstraZeneca and their patient journeys. And so what they have is medical records from patients for a 3-year time period. They have tens of billions of nodes representing patients, interactions with doctors, prescriptions, diagnoses, drugs they've been prescribed. And they want to understand the structure of that graph in order to identify the patients who will benefit from a new drug. So which patients have the graph structure associated with them to get a benefit from prescribing this drug. And they also looked at which providers should they interact with in order to make sure that information about those new drugs gets out. And so using algorithms both to train a custom path embedding for predicting patient outcomes, as well as a more typical kind of marketing use case of who's most influential. One data set can answer multiple questions. And so with that, I'm going to pass it over to my colleague Stuart to do a live demo of what this actually looks like in practice.
Great. Thanks, Alicia. So in the demo, we're going to have a look at the Marvel universe, the Marvel social graph. We're going to use our supervised machine learning to predict a couple of things. So we're going to predict whether any of the characters are missing the label X-Men or who could be X-Men. And we're also going to predict some relationships, who might appear together in future comics events, whatever they might be. So as we do that, we're going to take us through a few steps. We're going to firstly review the graph, see what we've loaded into Neo4j. We're going to do some feature engineering. We're going to train some graph embeddings, and as I say, we're going to get to our fun predictions. So to explore the graph, we want to see, what we've got in the data set, and we can start to see things over on the right-hand side. We can see that we have our characters, our comics, events, and groups. And if we look at the relationships, we can then see, all the different relationships that each person has. So a character would, appear in a comic with part of event, part of groups. So that gives us our kind of data model. So exploring it a little bit, we can do characters. And given that we're thinking about X-Men, let's do characters that belong to the group with the name X-Men. So this gives us a nice, easy way to kind of get in to start exploring the graph. And we can, see the graph come out here. So we've got X-Men in the center. Then we've got, all of the people who have been flagged in the import as being X-Men. So that's great. We can start to see those. You can see, there's different sizing for these nodes. That's actually set up as a style. So we can do things like, size by all the different properties that we have for the characters, for example. And if we do have a look at that, let's have a look at Colossus. We can start to see, some of the bits of information that we have. So we have, scores like durability, energy, fighting skills. So they're all their kind of stats or skills, basically. But then, we might want to start exploring this a little bit more. So if I'm interested in our characters, maybe let's expand, what events they're all involved in. This gets super fun in the visualization because we can start to see things like what are central events or, who are central characters. And the central characters, even though we're not done anything really, we've not run any features, we've not run any algorithms, we can, immediately start to see that some of these people are involved in lots and lots of events. So they're essentially going to be our central characters. And we can see, as we look at them, people like Colossus, Professor X, Storm, Logan, Rogue. We can see all of those, are in the films that everybody knows. So that gives us a great start. We can kind of see our model. Now we want to get in and start generating features and doing predictions. So moving into Neo4j browser, where we can actually kind of run our Cypher, our kind of queries, we'll see again the same kind of model. So this is just a different representation of the model. We can see we've got our characters and all the different types of relationships. And here we can actually also see that we had a different node in that we didn't display in Bloom. So in Bloom, where we saw a second ago, you can control which bits of the graph you want to expose. So we see, all of the same information, and same on the left-hand side, we start to see, what the relationship types, node labels, and properties are. So what are we going to do? Where are we going to start? Well, the first thing we want to do is project the bit of the graph that we're interested in so that we can start to run the algorithms that we want to generate the features that we're going to use in later. And so what this does is kind of load whatever subset or all of the graph that we want into an analytical workspace and in-memory graph. So here we're deciding to say, we want to only really load the characters. We want to load the specific properties that we're interested in. In this case, they're the ones we saw a second ago. And we also want to load in some of the relationships. And you see we've got, a fair amount of control here about, how we take the data that's stored in the underlying database and bring it into that analytical graph. So here we can see, we're specifying relationships, what directions we want, whether we want any aggregation on them, and any properties as well, things like that. So we can run that, and that's going to create an in-memory graph that we can then use in the next step. And what we're going to do next is calculate some features I mentioned. So we're going to look at pretty much centrality. We're actually going to look at a few different types. So again, I can set this running. And what it's doing is running PageRank. It's running it on the graph we just projected. It's running it on different relationship types. So we're actually calculating different PageRank scores based on the network with those different relationships. And what we see here is that we're also kind of running it in mutate mode. So what that does is it updates the analytical graph, the in-memory graph, with the output of the algorithm. The other options, of course, stream, so that would stream it back out and not, store it in the in-memory graph or in the database, or write, which would, write it back to the database, so we've got that data persisted. But because we want to, play here, we can just do it to the in-memory graph. So we're going to do pretty much the same again for betweenness. So now we've calculated betweenness for all of those three different relationship types, and then we're going to use a third centrality metric, hits. So we're going to calculate those. And so with that all done, what we've got is now, a number of new scores based on, the network structure, based on centrality algorithms. Of course, when we generate features, there's often a combination of different algorithms that we run, but also straight cipher. So, we typically characterize the algorithms as being kind of more graph global network analysis, and cipher, we can run to do much more kind of local things like what's happening 2 or 3 hops away from a node. So we can do that, and what we're going to do now, because we did do that mutate in the in-memory graph, is actually going to write all of these back to the main graph. And you'll see, all of these properties start to appear on the left-hand side because we've just written them back to the database. They're now stored and persisted. So that's, generated a few different features. We can then use those features that we created in our fast RP embedding. So our fast random projection, and this is an extended version which actually takes into consideration properties. And you can see all of the properties we've got. So again, we've got those base properties that we had to start with, plus all of the properties, all of the features that we've just generated through the algorithms that we ran. And you'll see it's giving us an embedding of 250 elements. So we do that, and then what we can do is just actually a little bit tidy up, to be honest. You can, in Neo4j, create, many different analytical graphs in memory. So that's fine. I mean, that's great. That's actually really good for, people working together or, trying out different ideas. But we always like to, tidy them up at the end just to make sure we're releasing that memory back. And now we've got the fast RP embeddings, we can train our node classification models. This is a bit where we're going to predict, based on the information we have, can we see if there's any people that are missing the X-Men label that should have it. So of course to do that we need to, label our data. So we can, label the people who we know are X-Men, they're part of the group X-Men. We give them that additional property. We can then see if we can label people as, explicitly not X-Men, and then get some holdout data. So anything that isn't already, in the model, we can now use as holdout data that we're going to predict on later. So now we've done that, we can again load our graph that we're going to use for predicting on. And we see here we've got 2 different sets. So we've got our model data, which are our training set, and our holdout data for the holdout character. So we can train the node classifier. And here we can again see how we trained it. So we're picking out specific labels, we're giving it the model name, we're giving it the features that we're going to use. Then we're going to tell it, what our evaluation metric is, so F1 weighted inaccuracy, and things like penalties. And as the output we get, of course, our train score and our test score, which they're both pretty high in this case. And if we wanted to, we could do a quick comparison, right? We could say, actually, if I wanted to compare that to just the things that we saw right at the beginning before we started calculating any of our graph features, just our energy, speed, strength, durability, intelligence, we could do pretty much the same thing. And this time you'll see, that the train and test scores are much lower. So we can see that we're getting, a better representative score using the graph features. So let's see what it might predict for us. So we're going to now predict using that same model and our holdout data. And then we're going to have a look at what the output is. So these are the things that it's predicted. And we've got obviously the probabilities as well. Of course, whether these are actual X-Men and we've predicted them correctly, we'll leave that as an exercise for the listener. Unfortunately, my actual knowledge of Marvel isn't that great. We can now start to think about training our link prediction model. So again, training to see whether we can, predict future relationships. And it's going to be a pretty similar approach that we did for the no classification model. So we're going to split the graph into our different sets. We are then going to create our model. So again, loading all of the properties that we're interested in. And then we're going to apply those splits to the in-memory graph. And we provide some algorithms to help you create those test and training sets. So with that done, we can train our model again. And this one will take a little bit longer. Obviously, it has more to do. But again, we see, the various settings that you can alter. Those are all in the documentation, so it's, obviously something that you'll want to experiment with as you go through using the models. But within a few more seconds, we should hopefully see our sets. So once we've trained, of course, we can go straight into predicting. So we're going to do our prediction on our holdout data, and we're going to write that then back to the graph. So we now see a new relationship appear on the left, appeared with predicted. That's our new relationship that we're predicting. So we can have a look at the raw results of those. That might be interesting. We can see that it's predicted that these sets of people will interact. And we could do something that's a little bit more fun. So instead of just saying, this person might interact with this, you see, people repeated quite a lot in the columns because they, potentially have lots of new interactions. But we could group that a little bit differently, which will probably be a little bit more fun. We can group that by, our person and then all of the characters that we're predicting they interact with. So I guess, the interesting thing about this output could be that, if we're looking for, the next series of films like the Avengers, that, we really want to build, lots and lots of smaller films around. And if we're a Marvel boss, we might say that this, this could be an interesting result, because we might want to, build our story arc around this person. Knowing that they've got lots of interactions with other characters as they as they go forward, so it'll be a great starting point to kind of build a story arc around. So that's great. I mean, that's all I really wanted to show. So very quickly we saw algorithms for creating features, and then running a couple of quick prediction routines. So obviously no classification, link prediction. So with that, back over to you, Alicia.
Okay, great. So I think, am I sharing my screen? So now that we've finished the demo, we can go on to resources. Lots of places for you to get more information about how to use Neo4j and the Graph Data Science Library. White papers, videos, case studies about some of our users. We also have a bunch of books that you can go download for free, from the Graph Algos book, as well as Graph Data Science for Dummies. And we have a sandbox and so much more for you to test out and get started. And with that, we can go and toggle over to questions.